Hello, I'm Michael Hyde, and I'm going over the Physics 2211 Lab 1 about constant motion. Now, here are some questions that you guys might have. First off, what is this lab about? Well, this lab is going over the constant motion of a rolling object. This is a panda who does not have constant motion. However, our object is one that rolls, and we are going to be testing what it is when forces cancel out to cause a dynamic motion problem where the object is in motion but has no net force. Now, what is constant motion? This is not constant motion. What is constant motion, however, is when velocity is maintained through the negation of friction, of momentum, and of every other force that could be acting on velocity in one or all directions. Now, what are forces? Great question. Forces are the action of some outer force interacting with the object. These are derived with the formula F equals mass times acceleration, where F is equal to the force. And we use these to denote changes and acceleration in motion of objects. Now, this is our experiment or our study where we are rolling what appears to be a spool of yarn. And this is the image of my tracker tracking along the path of it. We are testing it on a 1 meter long distance to find that constant velocity. Now, here are some important precursors. This impulse at the very start, where it is pushed, is called an impulse because there's no lasting force being acted on the object, which is the same as having no net force. And while there will be friction and momentum in the real world scenario, where momentum is P equals mass times velocity, and friction is mu times the same. And there will be friction in that, which is why our tracker will have some different data. However, they cancel out in the computation. Otherwise, the goal is to see the constant motion and see how velocity graphing trends. Now, here's our data. As you can see, we have x versus t on the left and position versus time on the right. The one on the left is the tracker data, as you can see by the wobbly line that follows. And this is because of different forces and different discrepancies in the calculation that we use to track it. And you can see that by the slight curve as well. And on the right here is my position versus time from the computation in the ideal. Much smoother, purely computational, and avoids all the real world discrepancies. Now, here are some of those discrepancies I was talking about. We interacted with some tracker issues where every time you did a manual input of location, of time gap, and of all the other data it needs, there were some chances to falter with the data and cause a bit of a difference in the points that were evenly spaced. And some other choices were the computational ones and assumptions, which were we assumed that there was no friction and we assumed that there was no momentum. However, to compute, I did use v final and v initial, which did cause a bit of a curve. Now, here's our what if, which is we rolled the object in the positive x direction and we chose to align the axis in that same way. However, if we flipped the x and negative x directions, the only difference would be slope, where the slope would be flipped as well, since it is constant motion and the velocity is a straight continuous line. Now for the conclusion. While this test was to test constant motion, we could see some differences in the way the data was allocated. And while it is possible to negate all the forces, momentum and friction canceling out, I used the tracker velocities to compute my hypothetical, which did cause that slight curve. Overall, this was a very interesting experiment, and I did learn a lot from the interaction of physics in the real world. Thank you.